Hal has been to my house like 3 times.
And you
Hal
trust
is
him?
actually extremely evil.
Yeah.
No, I've met the man. He's extremely evil. He's very quiet. He listens more than he talks. But you can tease things out of him, but it's only what he wants you to tease out of him. He's like a nice old grandpa. Like you talk to him and he's like quiet and sweet and gentle like a nice old grandpa, but he's evil as it's creepy.
What is Hal Puthoff trying to accomplish in this paper? What does he actually argue? What does this paper actually contain as far as content? It is very mathematical. Like I said, it does not prove the existence of zero-point energy field. It gives a suggestion that assuming you have a framework that involves the zero-point energy fluctuation field, then this can account for legitimate phenomena which are traditionally conceived of as being explained as quantum phenomena. So while it doesn't prove that zero-point energy, zero-point field exists, it's starting to build up strength to the argument that it would be worthwhile to come up with a more rigorous, perhaps experimental vindication or observation of the zero-point energy fluctuations. So if you could accumulate these kinds of results, then that would be accumulating weight in favor of supporting that there is zero-point energy field out there. This paper, by doing the derivation, having the mathematical results for this equilibrium for the electron that's orbiting the ground state of the hydrogen atom, that's just one drop in the bucket of weight of support for the larger argument, you could say, of saying that the zero-point energy field exists at all in the first place. So it's not, an experimental evidence drop in the bucket necessarily, but it's connecting pre-existing dots of experimentally available results, things that Niels Bohr at his day and age did in order to lend weight to his model of the atom, which involved quantization. It's part of the early quantum theory. Hal Puthoff is saying, we're going to rewind, we're going to go back to that forking off branch point. We're going to take from the late 70s, early 80s, Tim Boyer's stochastic electrodynamics. We're going to postulate this zero-point field, and we're going to branch off. We're going to go in a different direction than where traditional modern mainstream physics went with Bohr and Bohr-Sommerfeld, and then we get Schrodinger's equation, and then we get Heisenberg matrix formulation, blah blah blah, Dirac, Pauli, and we do all this stuff. He's saying we're going to go back, we're going to use stochastic electrodynamics to connect the dots at the level of the Bohr atom, and this is a drop in the bucket of suggesting that zero-point fluctuation, zero-point energy, this is something that can be taken somewhat seriously. So what does he actually show in this paper, being that it's a mathematical derivation? And right here we have equation 9, which is a little bit of a behemoth, spelled all out. The expectation value, or the average power absorbed from the zero-point background, is equal to 1/2 times the real component of the entire angle bracketed quantity, which is E squared over m. Bonjour tout le monde. It's been a while since I've made one of these more serious, sciencey, mathy videos. I've still been tinkering with my apparatus. If you want to know how I've been doing on that, you can obviously go watch any of my tinkering vlogs. But most of my videos haven't been getting a lot of views recently, and I don't really care because that's not what motivates me to do this whole YouTube thing. I just want to make videos just for the sake of making videos like the one you're watching. But with that being said, I do appreciate it if you like the video, if you subscribe, and leave a comment for whatever reason you want. But particularly in this video, since I don't have a formal background in physics, if you do have a formal background in physics, or if you have more expertise in physics than I do, if I make a mistake, if I say something that's incorrect, please comment down below. I would love to hear your thoughts and feedback on what I have for you today. So what today's video is going to be is a walkthrough of Hal Puthoff's 1987 paper titled Ground State of Hydrogen as a Zero-Point Fluctuation Determined State. So I have my physical copy here, and I'm going to do a quick run through of some slides to sort of give a background intro to the paper, and then I'm just going to basically read through the paper. All right, so what is this paper about? And I figured I would start off with a quote from Ernst Rutherford from 1914. He's pictured here on the right, and of course the Rutherford scattering experiments showed that the atom has most of its mass in the nucleus at the center of the atom, and that this is where all of the positive charge is localized, and there's a relatively large radius outside of that nucleus where the electron or electrons can be located. And so Ernst Rutherford was one of the figures who was at the forefront of developing the notion of the atom, and he was sort of at the tail end of the classical era of electromagnetics, which, in contradiction to results of experiments such as the Rutherford scattering experiments, which were going on at the time, sort of motivated going beyond just the Maxwellian understanding of E&M. So the quote from Rutherford is, "I have so far not dealt with the important question of the distribution of the external electrons which make up the atom. It is obvious there are great difficulties on the ordinary mechanics in considering possible distributions, for there is no reason why an electron, if disturbed, should not always fall into the nucleus." And I have pictured down here in the bottom right this problem which Rutherford was referring to. If you have this electron which is initially orbiting your nucleus here of the atom, then by Coulombic electrostatic attraction, then that electron attracted by the nucleus will spiral inward in an accelerating fashion, and due to this acceleration it will emit electromagnetic radiation. The expectation is that the photons of this electromagnetic radiation will be of a continuous spectra, and the electron will eventually plunge into the nucleus. And so one of the problems is that there is a stability of matter which is observed. That is, electrons don't just plunge into the nucleus. And second of all, there's the observation of the discrete spectral lines, whether it be of the emission or the absorption of atoms. They're complementary to each other, so in a way you can tend to focus on just the emission spectra. We'll get into a little bit of that in a sec here. But this is basically the problem, because this is more or less expected from a classical Maxwellian viewpoint of E&M. So what is this paper then about? Well, it's basically about Hal Puthoff showing that one way of thinking about why the electron doesn't fall into the nucleus, instead of ad hoc quantization, which is what Niels Bohr did in the Bohr model of the atom, you could consider it as a balance between the time average radiated power and absorbed 0-point fluctuation power. So basically it's the idea that the classically expected radiated power from the electron plunging into the nucleus is balanced by absorption of power from 0-point fluctuation. So Hal Puthoff's calculation that he shows in the paper leads to the equilibrium radius of the ground state of the hydrogen atom, that is to say the electron in the 1 proton 1 electron hydrogen atom. The electron is not in an excited state, so the principal quantum number n equals 1. He basically is able to more or less allude to recreating the Bohr radius of the hydrogen atom, but really the core calculation comes down to m times omega times lowercase r squared being equal to h bar being the Planck constant divided by 2 pi. We have m being the mass of, I believe, the electron. Omega is, of course, angular velocity, and r is the Bohr radius of the hydrogen atom. So this m omega r squared equals h bar relation is calculated in this paper at the level of theory of the Bohr atom, but specifically Puthoff does not invoke ad hoc quantization, which is what Bohr did. Bohr invoked, of course, you can call it the Einstein relation or the Planck relation for the discretization of quantized energy states. You have the whole E equals HV relation, and we'll get into more details of that in a sec. But instead, Puthoff conceptually grounded his derivation on Timothy H. Boyer's Stochastic Electrodynamics framework, SED here. And so SED incorporates the stochastic, or that is to say random background electromagnetic field, which is the 0-point fluctuation, to reproduce many quantum phenomena. Particularly in this case, we're looking at the ground state of the hydrogen atom, classically, that is to say, without the typical quantization of matter or fields. So to give a little bit more of a summary of the paper, within stochastic electrodynamics, the hydrogen ground state can be modeled as a dynamic power balance equilibrium, as I said. And at the semi-classical Bohr level, which postulates circular orbits, the electron undergoes centripetal acceleration and radiates according to the Larmor formula. I didn't write it here because we don't have enough space. You could think of this, I guess, as kind of like a planetary model of the atom, where the nucleus of the atom is like the sun, essentially, and the electrons are like the different planets orbiting the sun. However, it continuously absorbs energy from the fluctuating 0-point fluctuation field via the dipole interaction. So this balances the centripetal acceleration that is expected to lead to radiation as the electron is plunging into the nucleus. This is what prevents that, the ZPF field, imparting energy into the system that way. So setting the time averaged absorbed power equal to the radiated power yields a stable equilibrium precisely at the Bohr ground state parameters. So we're able to recapitulate the Bohr radius, lowercase a naught, frequency omega, and the angular momentum of the hydrogen atom given by m omega r squared equals h bar. And you could have the statement for angular momentum being m omega r squared equals n h bar, but we're looking at the ground state, the true ground state, so n equals 1. This resolves the classical radiative instability without ad hoc quantization, as I said. This was one of the things that bothered even Ernst Rutherford in his time. We'll have a little bit of a look here in a few slides of some of the history of the model of the atom to give it a little more context here, but the derivation that Puthoff gives parallels quantum electrodynamic results for linear systems, and it shows that the 0-point field is causally responsible for preventing the collapse of matter. So that's, I guess, a little bit of a long-winded summary of what this paper is all about in a nutshell. I will say that a major caveat to this is that showing this derivation does not prove the existence of the 0-point energy field by any means. Really, it's just showing that Boyer's framework of stochastical electrodynamics and postulating the presence of a 0-point field are valid ways of sidestepping a lot of the major tenets of quantum theory, which would otherwise be thought to be necessary to explain so-called quantum phenomena. And we'll list off some of these here, but to give a little bit of a foreshadowing, those include the Planck blackbody radiation spectrum, Casimir effect, van der Waals forces, and the thermal effects of acceleration through the vacuum. So if you're accelerating through the vacuum and you perceive being in a thermal bath, those things are typically explained by a quantum framework, but through papers such as one we're going to go over today, Hal Puthoff and others have been able to show that stochastic electrodynamics and postulating the presence of this 0-point field can sidestep the orthodox quantum explanations for these phenomena. So here's a little bit of a background on Hal Puthoff. He is currently the managing director at the Institute for Advanced Studies in Austin. He is quite distinguished, and his research has had three main eras. After he got his PhD, in the 60s and 70s, he worked on quantum electronics, and then he started his whole career in black worlds projects, you could say. In the 70s and 80s, he worked on parapsychology and remote viewing. This included working with people like Ingo Swann, of course, and that's its own, topic that you could dive into, a whole rabbit hole. And the third era of Hal Puthoff's research has been on zero-point energy, gravity or anti-gravity, general relativity, stochastic electrodynamics, and advanced propulsion. And this work, in some ways, it kind of started with this ground state of hydrogen as zero-point fluctuation determined state paper. This paper we're going over today was from 1987. So really, this is at the beginning of that third era of Hal Puthoff's career. And I looked up on his Google Scholar or something like that. Hal Puthoff has 78 public publications, racking up a total of 2,727 citations. And so as far as that third era of research is concerned, and what might be a little mini series here of going over some of these publications of Hal Puthoff, we have these selected works. So today we're looking at from 1987, ground state of hydrogen as a zero-point fluctuation determined state. 2 years later, he has a paper titled Gravity as a Zero-Point Fluctuation Force. 1997, Physics of the Zero-Point Field, Implications for Inertia, Gravitation, and Mass. He is the author of the DIRD paper 15. DIRD, of course, stands for the Defense Intelligence Reference Document. He authored, there's I think 38 or 39 of those papers. He authored paper number 15, which is on advanced space propulsion based on vacuum space-time metric engineering. Hal Puthoff has actually talked in public about how that's kind of one of the things that scientists and engineers could be focused on related to all of this, this area of research and development, which is perhaps things are at a point where the effects are understood from a theoretical standpoint, but now the task is to do the engineering and implementation of devices that can accomplish the space-time metric engineering or manipulation. So then the last little selected work here from Hal Puthoff that I noted down here is he wrote chapter 18 of the book Frontiers of Propulsion Science, which was compiled by Mark Millis and someone you may have heard of, Dr. Eric W. Davis. So Hal Puthoff wrote chapter 18 of that book, which is titled On Extracting Energy from the Quantum Vacuum. So this just kind of gives a general perspective on how established and perhaps the weight of Hal Puthoff's reputation is currently now in 2026, as of recording this video, that we can look back from today's perspective on what could be considered maybe the start of Hal Puthoff's work in this area in particular, with his ground state of the hydrogen atom paper that we're going over today that he published in 1987. That was now about 40 years ago. So just a little background on the man himself, the author of this paper. I feel like it helps for the background of everything to just have some quick bullet points on tenets of stochastic electrodynamics. In this framework, which was established by Timothy H. Boyer, he is a professor at the City College of New York City. He's been there since the 70s. In this framework, classic Maxwellian electromagnetics holds, so Maxwell's equations are still valid. I think within this framework, the caveat is that they are formulated to include stochasticity instead of just being, these continuous non-random system of partial differential equations in, classic electromagnetics. In SED, the vacuum is postulated to be filled with a random classical zero-point radiation, which is homogeneous, isotropic, and Lorentz invariant. Well, this will be mentioned in the paper. So what do we mean by the radiation being homogeneous, isotropic, and Lorentz invariant? Well, homogeneous radiation is uniform in its distribution as far as the energy or particle flux is concerned. And the intensity, the fluence, the flux, and spectral properties of this radiation remain constant at every point in space. So the radiation being homogeneous means that it is uniform at every point in space. Isotropic means that the radiation strikes targets equally from all directions, every direction. So isotropic means that the radiation is uniform in every direction. So again, homogeneous, uniform at every point, isotropic, uniform in every direction, and Lorentz invariant, which of course means that the quantities remain unchanged by the Lorentz transformation. They're the same for all observers regardless of their constant velocity or spatial orientation. Interactions between charged particles and the fluctuating zero-point radiation produces effects that mimic those from quantum mechanics, as I sort of mentioned a little bit. And stochastic electrodynamics is statistically equivalent to quantum electrodynamics, QED, in many regimes. So, being that Hal Puthoff's paper is aiming to resolve the issue of radiative collapse at the level of theory of the Bohr atom, at which he's invoking this stochastic electrodynamics framework, it helps, I think, to have a little bit of a context of the historical place that the Bohr model of the atom has with respect to models that came before, models that came after. So after Maxwell had cemented his 4 equations governing electricity and magnetism, there was still a lot of a debate on what the nature of electricity even was, what the nature of magnetism is, and alongside that, what the exact nature of the atom is. If you look at my Gray Alien Discusses the Photoelectric Effect video, I kind of touch on some of these things. Some of those things were touched on, around the turn of the century, around 1900, there was beginning to emerge an abundance of experimental evidence that in some ways contradicted the expectations of classic Maxwellian electricity and magnetism, and it sort of necessitated the emergence of a new quantum framework. But along with that also comes necessitating a conception of atoms and subatomic particles. At this time, there was also the emergence of chemistry as a field proper in response to some of these questions, especially related to the nature of atoms and molecules, and the emergence of physics as a proper field and discipline. And so one of the early emerging notions of what atoms were was that atoms and molecules are knots and vortices in the ether. And there had been the development at the time of this contraption here by, I think, someone named Tait, last name Tait, T-A-I-T, and it produced smoke rings. This inspired people such as Lord Kelvin to hypothesize that atoms were akin to such smoke rings. They're, just knots and vortices in the ether. This idea was abandoned because as people like Dalton, working in what we now refer to as the field of chemistry, found out, is that there are more fundamental elements, for example, that we see now today in the periodic table of elements, than there are permutations of different knots. So that's to say the topology of knots and vortices mathematically is insufficient to describe the number of unique chemical elements that are actually observed in nature. So that's one of the things that led to the abandonment of the early atomic model that atoms and molecules are knots and vortices in the ether. So following this, we have J.J. Thomson's so-called plum pudding model. So he never actually called it a plum pudding model, and that's really just like a pedagogical, historical inaccuracy to call it the plum pudding model. That's just kind of hung around and ossified at the levels of like middle school education, your first ever exposure to chemistry, where your teacher isn't like this, very historically minded person. They just read the lesson plan and say, oh, it's called the plum pudding model. That's just what it is, everyone. So J.J. Thomson's model of the atom was not really called the plum pudding model. But anyways, the idea is that the atom is akin to a spherical shell within which all of the mass and positive charge is localized, and the electrons are smaller corpuscles which are uniformly distributed on the surface or the boundary of that shell. And of course, this model was cast in doubt by results such as Rutherford's scattering experiments, where radiation was aimed at a thin metal foil, and the scattering of the incident radiation, due to the relatively small area that the nucleus of the atom is localized, this scattering that was observed by the Rutherford experiments cast doubt on the prevailing Thomson model of the atom at the time. So another one of the things that these early models of the atom had trouble reconciling was the spectral line data from different chemical elements at the time. So when you excite the electrons of these particular elements, you observe a discrete set of spectral lines which are unique to whatever element is being excited that you're observing these spectral lines upon. And kind of like how I mentioned at the beginning, this is not what's expected in a purely classical view of the atom as far as being constituted by protons and electrons, because if you put the matter of the stability of atoms aside, then as the electron is accelerating into its plunge into the nucleus, then the emitted radiation would be at a continuous spectra of frequencies, which is not what's observed, because spectral lines are observed to be a discrete set of unique wavelengths corresponding to whichever element, like I said, has the excited electrons and its emission spectra is being observed. So one of the big breakthroughs in explaining the spectral line data was from Niels Bohr's model of the atom. I'll talk about that a little more on the next slide. But it basically postulated that electron orbits are circular and they're stable, and so electrons are confined to these orbits in which they're not gaining or losing energy. The exchange of quanta of energy only occurs when electrons move between these discretized circular orbits. The Bohr model was eventually expanded to include elliptical orbits. That's known as the Bohr-Sommerfeld model. But the model of the atom progressed further from the Bohr model, because shortly after the Bohr model of the atom was put forth by Niels Bohr, there was still greater advances made in early quantum theory. So one of the big advancements was, of course, made by Schrödinger. He comes up with the Schrödinger wave equation, which basically is this second order PDE. It's reminiscent of the heat equation, so it's a dispersive equation. When I say that it's a second order PDE, it has a second order derivative as its dominant operator, I guess you could say. The difference between the Schrödinger wave equation and, say, the heat is that the Schrödinger wave equation has, in addition to that second order derivative operator, it also has a first order time derivative, which has an imaginary coefficient. So qualitatively, it's very similar, because if you have, for example, the traditional wave equation or the heat equation, then you use the heat equation or the wave equation to update how the wave is dispersing through space and time, the dynamics of that, how the heat in 3D space is dynamically updating through space and time. So the Schrödinger wave equation is this, you could think of it as like a quantum operator operating on the quantum state. the wave function. And so you could get into the whole whether or not we're going to include in the fundamental furniture of the universe the wave function or not in its multidimensional aspect. That's a whole other can of worms. But after the Bohr model of the atom, the Schrödinger wave equation was like a huge step in developing quantum theory. So I guess the gist of what these pictures at the bottom of the screen are supposed to be showing is that on the bottom left, this is showing spherical harmonics, so solutions of basically like just the Laplacian for different parameters. So there's no Schrodinger's equation, there's no quantum anything underlying this picture. But then this image gets updated to what's in the bottom middle when we modify spherical harmonics to be then spherical solutions of the Schrödinger equation. That gives us the accepted orbital shapes. So the red top row is the s orbital, the next row is the shapes of the p orbitals, then the next row in blue are the d orbitals, the bottom row are the f orbitals. So we have the s, p, d, and f orbitals. These are for no particular atom or molecule. Like I said, it's just spherical solutions of the Schrödinger equation to come up with these generalized orbital shapes. And then on the right, since the hydrogen atom is comprised of only one proton and one electron, then these spherical harmonics of the Schrödinger equation can be solved exactly for the hydrogen atom. If you go to atoms with higher atomic number, then you're going to use numerical approximations, but you can get analytic solutions for the hydrogen atom. And so these heat maps show the probability of finding the electron at any point in space given the particular quantum numbers which you're solving the spherical Schrödinger equation for. So the different quantum numbers I'm referring to are like the principal quantum number, which is thought of as akin to the Bohr atom. What is the level of excitation? N equals 1, 2, 3, 4, 5 of your electron. But then other quantum numbers include the like the spin or like the azimuthal orbit numbers. So I'm forgetting what they all are. There's like the principal quantum number, the spin moment, and I think there's one more. But anyways, they're L, M, and N are what those quantum numbers are. But anyways, so when you have different values of L, M, and N, the different quantum numbers that you're then solving the radial solution of the Schrödinger's equation for, you get these different probability densities for where you're going to likely find the electron with respect to the proton at the nucleus of the hydrogen atom. So these different values of the quantum numbers L, M, and N will give you the different shapes for the probability densities of the different electron orbitals. So to give a little more background on specifically the Bohr model, since this is, like I said, the level of theory that Hal Puthoff's derivation, where we're equating the power radiated by an electron that normally without any other fields being present would be expected to plunge into the nucleus, that emitted radiation is balanced by the absorption of radiation from the 0-point field. This derivation is at the level of the Bohr model of the atom, like I said. So as I kind of alluded to in the previous slide, there are more sophisticated or advanced, you could say, models of the atom that Hal Puthoff could have considered, but he didn't. So it's important, I think, to understand more details of the Bohr model in order to appreciate perhaps why Hal Puthoff did this in his stochastic electrodynamic 0-point fluctuation derivation in this paper. So I may have already mentioned this a little bit, but I'm just going to recapitulate it again to be clear. In the Bohr model, orbits of electrons in atoms are quantized and closed. So when I say quantized, that means that emission and absorption are going to be subject to delta capital E equals lowercase h times lowercase f. So the change in energy during emission or absorption of the quanta of energy is equal to Planck's constant, lowercase h, times frequency. So this frequency is determined by the frequency of the light of the photon which is emitted or absorbed in this exchange of a quanta of energy. So by postulating that orbits are quantized and closed in this way, then no energy could be lost by the electron when it's in orbit in the atom. And as I said, when there's this exchange of a quanta of energy, then this explains the sets of discrete spectral lines which are observed from excited atoms. The spectral lines which are observed are then interpreted as the transitions of electrons between these particular closed quantized orbits. So on the right here, far right, here's a picture of Niels Bohr himself, but at the near right here to the text, there's this depiction of such closed quantized orbits. And so if you have, let's say, an electron which is initially at the n equals 5 excited level and it decays down to the n equal 2 level, then for the hydrogen atom, you'll observe a 434 nanometer wavelength violet spectral line. And when an electron from the n equals 4 state transitions down to the n equals 2 state, then that results in the 486 nanometer green wavelength spectral line. And when an electron similarly decays from the third to the second level, you get the red spectral line. And so these wavelengths, they of course obey at the time the empirical relation given by the Rydberg-Ritz combination principle. But these wavelengths are dictated by, one, what are the exact strengths of these energy levels of these different orbitals, and then what is the radius of the energy levels. And so implicitly from this, there's also, what is the, for like the case of just a hydrogen atom, what is the size and mass of just a proton. And so that's kind of why looking at these theoretical frameworks, such as the Bohr model of the atom, is kind of important in reconciling available experimental data, because you can do experiments which don't necessarily, commit or adopt to any particular framework, but you're just, developing in apparatus devices, conceiving of experiments so that you can just sheerly measure what the radius of a hydrogen atom is. What is the actual charge of an electron? What's the actual charge of a proton? Things like that. Then you can turn around with that experimental data. What are the actual wavelengths of the atomic spectral lines that you're observing? Turn around then and use that as a basis to develop your theoretical frameworks from, because if your theoretical frameworks can't explain these things, then that casts doubt on your theoretical frameworks. So, like I said, one of the advantages at the time of Bohr's atomic model and subsequently the Bohr-Sommerfeld model is that not only did it explain the available spectral line emission spectrum wavelengths for particular atoms, by having the postulate of closed quantized electron orbits, but then Bohr's model also gives us the Bohr radius of the hydrogen atom. And having things like the Bohr radius of the hydrogen atom go hand in hand with affirming, for example, like Planck's constant as well. So you could come at the problem experimentally from two ways. You could either presuppose a value for Planck's constant, h, or conversely h bar, which is just h over 2 pi, and then you can use that to affirm the Bohr radius of the hydrogen atom, and then look at that and say, oh, well, that calculation is then close to what the value of the experimentally observed radius of the hydrogen atom is. Or you could go backwards and say, well, given the observed radius of the hydrogen atom, what our measured value for the Bohr radius is, go backwards and say, oh, now look at how that somewhat affirms what Planck's constant is. But as was mentioned in my previous video, where there's the gray alien discussing the photoelectric effect, Planck's constant was experimentally vindicated by Millikan in response to Einstein's photoelectric paper, when Millikan doubted that Einstein was correct and ended up vindicating him And along the way, in his measurement of the charge to mass ratio of the electron, the slope of that line that Millikan experimentally observed, that is the determination of Planck's constant. So really you're going from take that value that's accepted, more or less accepted, quote unquote, of Planck's constant, and then that affirms the theoretical calculation of the Bohr radius, and then how that is within a tolerable regime at the time of what the observed value of the radius of the hydrogen atom is. Anyways, that's all to say there is a shortcoming. So not only does the pure Bohr model, let's say, have circular orbits, that's rectified by the Bohr-Sommerfeld model, which allows for elliptical orbits. It also incorporates like the action integral. Anyways, but the Bohr model of the atom assumes implicitly that the hydrogen atom is flat, because that's the only way to get these circular orbits. They're not spherical orbits. Okay, that's a critical distinction. And the particles in the Bohr model of the atom are assumed to be point-like. However, truly subatomic particles, such as electrons and protons, do embody 3D space. And so they do have volume, and that is to say they aren't points in the precise sense of the term. So this is a problem that is also underlying the non-relativistic solutions of Schrodinger's equation, which come up with the probability density functions. Oh yeah, also in this picture it says that the electron is falling from the given energy level to the n equals 2 ground state level. You could say, oh, well, I thought the principal quantum number n equals 1 is the ground state level. Well, okay, it says here at the bottom, the transitions from the n equals 6, 5, 4, and 3 levels to n equals 2 fall in the visible region. That's the key part here. Falling down to the n equals 2 energy level leads to emission spectral lines, which are in the visible region. These lines, so the violet, green, and red lines, which are observed for the hydrogen atom, these are called the Balmer series. So if I'm not mistaken, when an electron transitions down to the n equals 1 true ground state, n equals 1, then the spectral line is ultraviolet. It is not visible. And then I think that's called the Lyman series, Lyman. And there are all these other names for when electrons from higher energy orbitals decay down to, let's say, like n equals 3 or n equals 4, n equals 5. But when you're decaying down to a state that's greater than n equals 2, if I'm not mistaken, these will be then infrared. So it's only the Balmer series that correspond to transitions between these Bohr orbitals that lead to visible spectral lines. If you decay all the way down to the true ground state, n equals 1, rather than n equals 2 as it says in this little picture here, then you'll get ultraviolet. And then if you decay down to not the ground state, so from like n equals 6 to n equals 5 or something, then that'll be an infrared spectral line. And I think those are called the Paschen series. Oh, there you go. Paschen series, bracket series. Yeah, we've got Lyman series, ultraviolet all the way down to n equals 1. Balmer series, visible. Paschen, bracket, Pfund, those are all infrared. Paschen, bracket, Pfund, those are infrared, and it's transitioning from higher excited states down to still relatively lower states, but they're still relatively high compared to the n equals 1 ground state. Anyways, you could ask the question, why don't electrons decay into the nucleus from like a typical undergraduate first class in quantum theory, quantum mechanics? If you asked, a physics major who just took quantum mechanics for the very first time, and you ask them, why don't electrons decay into the nucleus? Give me your quantum theory, quantum mechanics explanation. They might say something along these lines. They would say it's due to the Heisenberg uncertainty principle. So first, we're going to abandon the idea that subatomic particles have well-defined trajectories in space. So we're abandoning the circular or elliptic orbitals of the old quantum theory Bohr model of the atom. And you can do this by the physical motivation of things such as the results of the Davison-Germer experiment, which, if I recall correctly, that's where electrons were bombarded onto a crystal structure, and the electrons scattered in a way that is reminiscent of the scattering of waves. So you have in the experiment electrons that are being scattered by a grating of electrons scattering electrons, and the scattering of the incident electrons is more reminiscent of the scattering of waves rather than the scattering of elastic particles. So the Davison-Germer experiment's results suggest that there is a wave-particle duality of matter. So this is going beyond just, for example, the photoelectric effect, Compton effect, or the Compton wavelength, which show that light has a wave-particle dual nature. But, these early old quantum theory experiments, such as the Davison-Germer experiment, also suggest that matter itself has a wave-particle dual aspect. So based upon this, we can abandon the idea that subatomic particles have well-defined trajectories in space, because you're thinking of them as waves, so they don't have these, well-defined local trajectories. You have to think of them in terms of de Broglie wave packets, etc., etc. So if you confine an electron to a smaller space, then that drastically increases its momentum and kinetic energy uncertainty, and eventually extreme confinement, that is to say to the size of the nucleus, as per would be expected when the electron is collapsing into the nucleus, this triggers massive kinetic energy. And this massive kinetic energy creates an outward, quote, quantum pressure, unquote, which overwhelms the Coulombic electrostatic attraction, which otherwise would have been responsible for the collapse of the electron into the nucleus of the atom in the first place. So if you wanted to make this a little bit more rigorous from a quantitative sense, then consider at the left here we have the formulation for the Heisenberg uncertainty principle. We have delta x times delta p is greater than or equal to h bar over 2. So delta x is the uncertainty in the position of the particle wave of the matter that is in consideration. Delta p is the uncertainty in the momentum of the matter energy in consideration. And then the product of these two uncertainties is greater than or equal to Planck's constant, h bar over 2. So when we consider this Heisenberg uncertainty relation in the context of an electron falling into the nucleus, then in the plunge to the nucleus, delta x shrinks roughly to the size of a proton, which, being that the right-hand side is conserved, then this leads to delta p becoming enormous, and it is then this high delta p, this high change in momentum, which outweighs the attractive Coulombic electrostatic force between the electron and proton, and this is what prevents the electron from decaying into the nucleus. So it's because of the conservation of energy, conservation of momentum, which is implied by the Heisenberg uncertainty principle, which that is what explains why at this level of, you could say, like undergrad quantum theory, quantum mechanics, why electrons don't decay into the nucleus. So we could get a little more technical. There's this reference here that I haven't really gone into much at all in detail, but it seems like a pretty strong resource to this end, by Lieb and Seringer. It's called The Stability of Matter in Quantum Mechanics. It's a very mathematical physics text. Apparently the question of the stability of matter in quantum mechanics is sort of like a big success for mathematical physics, and this book goes into very great detail in this. So if you think this is what I would call maybe like the most sophisticated level of explanation. It's probably not the most penultimate, most sophisticated explanation. I've left a couple links in the description below to some Stack Overflow threads, which do have more sophisticated discussion on explanations for the stability of matter and why electrons don't just spontaneously decay into the nucleus. I put those below, but this is sort of scraped from the highest levels of those discussions, you could say. There are two main considerations when you're answering this question of why electrons don't decay into the nucleus. One is you consider the stability against a collapse of the electron's wave function, and 2, you consider the stability against the electron's escape. So why doesn't the electron fall into the nucleus? Why doesn't the electron just float away from the nucleus? Okay, those are the two aspects that you have to consider to answer this question more thoroughly. So on the one hand, when you're considering the stability against a collapse of the electron's wave function as it's surrounding or it's entrapped by the Coulombic electrostatic attraction of the nucleus, the electron's wave function becomes bounded within an arbitrarily small distance from the proton. This is kind of what I mentioned on the previous slide as far as the Heisenberg uncertainty principle. And then there's the other aspect, considering the stability against the electron's escape. This aspect assumes a point-like proton. One of the problems with this, and this is kind of like I said, a problem stemming from going back to the Bohr model of the atom. Protons, of course, are not really point-like. So in the arguments outlined on the previous slide, compressing the electron to an arbitrarily small space, call it epsilon, near the center of the proton, gives an electric field whose energy diverges to infinity on the order of 1 over epsilon. And so if the proton were truly point-like, then the external field would go to 0 in this limit, and so this argument would fail. So to get around these issues, you could do a little bit of a dimensional analysis on two quantities which come up time and again in these considerations of the stability of matter. One is the fine structure constant, which is alpha equals lowercase k times e. I believe that should be squared if I'm not mistaken, instead of times. So it's ke squared over a denominator of h bar times c. So the fine structure constant alpha is approximately equal to 1 over a denominator of 137. Why is it 137? That's a big question. Who knows? So consider that first quantity, the fine structure constant, and then also consider the Bohr radius itself. Lowercase a naught equals a numerator of h bar over a denominator of mc times the fine structure constant alpha, where m is the mass of the electron. Okay, so I guess, yeah, I was wrong previously when I thought that m was mass of the entire hydrogen atom. Anyways, we're considering these quantities in order to eventually come to the conclusion or the suggestion that in order to rigorously establish the stability of matter, you need relativity and quantum field theory. So you need to go beyond just mere quantum mechanics, quantum theory. You need the additional tools of relativity and quantum theory. And you come to this realization by considering the dimensions of these physical quantities. So in hydrogen, the typical velocity of the electron is alpha times c, the fine structure constant, times the speed of light. And since this is small compared to the speed of light, then in some sense you don't really need quantum field theory for hydrogen. And still considering hydrogen, the Schrodinger's equation, which is non-relativistic, makes an excellent approximation in this case. However, once you go beyond hydrogen, if you consider a hydrogen-like atom consisting of a nucleus with atomic number Z plus a single electron, so you're adding more protons to the nucleus, but you're just sticking with just one electron for now, then the velocity in units of the speed of light is on the order of the atomic number capital Z times the fine structure constant. And as this is getting larger, you're approaching a quantity z times alpha, which is closer to the scale of lowercase c, the speed of light. And so for large z, then this shows that you really do need relativity, because not only will your electron be moving at relativistic speeds, but you'll also need quantum field theory to make these considerations. You need a dispersion equation for the quantum state, which is not the Schrodinger equation, because the Schrodinger equation is non-relativistic. In order to have these sorts of considerations for the stability of matter, when you have, something with an atomic number greater than 1, you're looking at things that are more than just hydrogen, you need the relativistic equivalent or analog of Schrodinger's equation. That is considered quantum field theory. And it's like I said, when the electrons are, in these orbitals, they're moving at speeds comparable to the speed of light, which is relativistic. So for large Z, you need relativity and quantum theory. So this is just to kind of allude to the notion that there is a whole deep dive that you could go out there. You could go to more sophisticated levels of considering these questions of why don't electrons decay into the nucleus? How do you explain the stability of matter from a theoretical physics point of view? You're going to need relativity, you're going to need quantum field theory, but that's not to say that the Bohr model of the atom is not without its merits. And the Bohr model of the atom was, in some sense, a turning point for physics, because it did include those new emerging ideas, results at the time of Niels Bohr, such as the abundance of spectral line data and the new tools from Planck and Einstein regarding the quantization of energy. So the Bohr model of the atom is not something that is worth necessarily just throwing away. The Bohr radius is still a reasonable approximation for the radius of a hydrogen atom, as well as giving decent approximations for the energy levels of the hydrogen atom. So that's why I think, in spite of there being these more sophisticated, modern descriptions and understandings of the stability of matter and the nature of atoms, subatomic particles, etc., the Bohr model of the atom is still worthwhile for Hal Puthoff's purposes in this 1987 paper, for saying, hey, we can take the framework of stochastic electrodynamics and its implicit postulating of the 0-point field in order to have this equilibrium balance between the emitted radiation of electrons as they transition from excited energy levels to the ground state. It's a reasonable place, I think, to jump off, especially because it was at the turning point of Niels Bohr's introduction of his model of the atom that energy quantization was introduced into the model of the atom, right? With the quantized closed circular, and then with subsequent Bohr-Sommerfeld theory elliptical orbits of electrons in the atom. So before I get into reading actually straight from Hal Puthoff's paper, I'm going to give a summary of what is mathematically derived in Puthoff's paper. Now that we have a little more of like a qualitative, holistic view of like what is Hal Puthoff trying to accomplish in this paper? What does he actually argue? What does this paper actually contain as far as content? It is very mathematical. Like I said, it does not prove the existence of 0-point energy field. It gives a suggestion that, assuming you have a framework that involves the 0-point energy fluctuation field, then this can account for legitimate phenomena which are traditionally conceived of as being explained as quantum phenomena. So while it doesn't prove that 0-point energy, 0-point field exists, it's starting to build up strength to the argument that it would be worthwhile to come up with a more rigorous, perhaps experimental vindication or observation of the 0-point energy fluctuations. So if you could accumulate these kinds of results, then that would be accumulating weight in favor of supporting that there is 0-point energy field out there. This paper, by doing the derivation, having the mathematical results for this equilibrium for the electron that's orbiting the ground state of the hydrogen atom, that's just one drop in the bucket of weight of support for the larger argument, you could say, of saying that the 0-point energy field exists at all in the first place. So it's not, an experimental evidence drop in the bucket necessarily, but it's connecting pre-existing dots of experimentally available results, things that Niels Bohr at his day and age did in order to lend weight to his model of the atom, which involved quantization. It's part of the early quantum theory. Hal Puthoff is saying, we're going to rewind, we're going to go back to that forking off branch point. We're going to take from the late 70s, early 80s, Tim Boyer's stochastic electrodynamics. We're going to postulate this 0-point field, and we're going to branch off. We're going to go in a different direction than where, you know, traditional modern mainstream physics went with Bohr and Bohr-Sommerfeld, and then we get Schrodinger's equation, and then we get Heisenberg matrix formulation, blah, 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 Dirac, Pauli, and we do all this stuff. He's saying we're going to go back, we're going to use stochastic electrodynamics to connect the dots at the level of the Bohr atom, and this is a drop in the bucket of suggesting that 0-point fluctuation, 0-point energy, this is something that can be taken somewhat seriously. So what does he actually show in this paper? Being that it's a mathematical derivation, there are about 8 steps from my view of what Hal Puthoff actually did in his derivation in this paper. So step 1, he gives the stochastic electrodynamic formulations for the electric field and the magnetic field. These are equations labeled 2 and 3 in the paper. Step number 2, substitute the formulation for the stochastic electrodynamic electric field, equation 2, substitute that into a non-relativistic equation of motion. It's labeled equation 4, which this non-relativistic equation of motion describes along the x-axis for a one-dimensional charged harmonic oscillator with mass m, natural frequency omega naught, and charge lowercase e, initially at the origin immersed in 0-point radiation, shows its equation of motion. It also includes radiation dampening. That's a mouthful, but the point of step 2 is we substitute the stochastic electrodynamic formulation for the electric field. Keep in mind, it's reminiscent of what's in the classical continuous, you could say traditional mainstream formulation of Maxwell's equation, but it includes that random stochastic element. So we take that formulation for the electric field, we substitute that into this non-relativistic equation of motion for a 1D harmonic oscillator with these given parameters. We're including radiation as well as radiation dampening. So by substituting the electric field relation into this equation of motion for a 1D particle here, we obtain 2 more relations, one for displacement, one for velocity of this charged particle. So we've taken the field equation, the motion equation, we've got a displacement and a velocity equation out of it at step 2. Next, using these, we calculate the average power absorbed from the 0-point background. We do this using the previously obtained velocity equation, and we again use the stochastic electrodynamic electric field relation. So we take equations 2, equation 6, we combine them. That's how we calculate the average power absorbed from the 0-point background. This is denoted by capital P with a superscript ABS. So it's power absorbed, and then it's enclosed in these angle brackets. And of course, enclosing quantities in angled brackets denotes that this is an expectation value. And another way of thinking of an expectation value is it's an average. So this gives us the first formulation of the average power absorbed from the 0-point background, and that is equation 9. So most of the subsequent steps are going to be simplifying and manipulating this expectation value for the absorbed power from the 0-point background quantity, which first shows up as equation 9 in the paper. Step 4, we simplify equation 9 into equation 10. We're just changing the forms of it. I'm not showing it right now because we're going to go into the paper in a little more depth here momentarily. We simplify equation 9 into equation 10 by averaging over random phases, which are given by equation 11. So it's just step 4 is a simplification step. Step 5 is also a simplification step. We use this integral identity. The integral of d3k is equivalent to the integral of d omega sub k times integral of dk times k squared. We use that integral identity to rewrite what we had simplified into the form of equation 10. We're able to rewrite that as what is given as equation 12. So steps 1 through 3, we obtain the expectation for the power absorbed from the 0-point background. Steps 4 and 5, we're just simplifying that further. We do that with these averaging over random phases given by equation 11 and using this integral identity. I already mentioned step 5. Anyways, step 6, you do the sum over polarizations given by equation 13. That transforms the angular integration in the K term, which was from equation 12 obtained at the end of, let's call it step 5. We get equation 14. Substitute equation 14 back into equation 12, and you take a change of variables according to omega equals Kc. That yields equation 15. So we're manipulating the integrands some more, the integrals that are in the relation as we're transforming our, that's the big picture, is through these steps 4, 5, 6, and 7. We're taking equation 9, which was originally obtained as our expectation for the power absorbed from the 0-point field. We're just doing these manipulations on the integral. We're averaging over the polarizations, etc. We do a change of variables. We're just getting this into a form where we can really get the results that we're looking for, get some strong results, what we really want here. Step 7, a small gamma. This gamma is a shorthand for this kind of big cluster of constants and variables, but it's basically at step 7 we're doing a mathematical step based upon an analysis of one of the physical quantities which is in what we're calculating here. So it's this argument where this small value of capital gamma, which we have in the quantity we're working with at this point, allows us to justify that the integrand of equation 15 is sharply peaked around angular frequency omega at the value of omega naught. So this allows us to invoke a resonance approximation and then to furthermore extend the limits of integration on what we're working with at this point. And this furthermore allows us to replace omega by omega naught everywhere except the difference term, which is present here. That allows us to obtain what is in the paper equation 16. So like I said, steps 4, 5, 6, and 7, it's mathematically manipulating our expectation value for the absorbed power from the 0-point fluctuation. So you could basically have your eyes glaze over at steps 4, 5, 6, and 7, and we've mathematically manipulated what is still physically, we're considering the same literal phenomena, quantity, the expectation of the power absorbed from the 0-point field. We're just putting it in terms where we can do what we want to do with it, which is in step 8 here. Step 8 has basically 2 parts. Part 1 of the final step here. From Bohr theory, we consider a ground state pair of 1D harmonic oscillators in the plane. That's relation 17. That leads us to a statement for the power absorbed from the background by an electron in a circular orbit, which is given in equation 18. The other part of the final step here of the derivation is we consider the power radiated by an electron in a circular orbit with acceleration denoted capital A. That's equation 19. So by Boyer's stochastic electrodynamic hypothesis, we then equate equations 18 and equations 19, and it is that final step which leads to the equilibrium relation which is being sought, which is m times omega naught times lowercase r naught squared equals h bar. So this is just saying that the angular momentum m omega r squared when the ground state is what we're at, so implicitly lowercase n is equal to 1. That would be on the right hand side here. We'd have angular momentum m omega r squared equals n h bar, but we're at the ground state, so lowercase n equals 1. This is just equal to h bar, right? So going through all these steps recapitulates this old quantum theory, classical quantum theory relation from the classical Bohr model. It's like, do you call it classical? Because classical could be, Maxwellian E&M, but from like a modern 2026 vantage, then the Bohr model of the atom could be considered classical. It's not really modern quantum theory, it's old quantum theory. Anyways, that is the relation that Hal Puthoff derives in this paper. And it's the interpretation, and it's considering all these steps, that's kind of like the physics underlying all of this stuff. Because really, what actually happened here? We have an expression for an electric field and a magnetic field that involves stochastic random terms. Substitute that into an equation of motion to get a displacement and a velocity equation. You combine the velocity equation with the electric field stochastic relation from the beginning, and you get this average power absorbed from the 0-point background. Then you do several steps of mathematically manipulating this, and then you use, in the final step, the classical Bohr theory arguments to then come up with the final statement of angular momentum equals n times h bar, set n equal to 1, and you get the energy at the ground state for this atom. So by achieving this result, m omega naught lowercase r naught squared equals h bar, this is what comes out from old Bohr theory when you just consider things like, oh, we're going to have energy equals the centripetal force being equal to the Coulomb electrostatic attraction, and then you throw into that relation things like the Einstein-Planck quantization of energy, E equals Planck constant times frequency. You can use that to obtain the same relation, but Puthoff in this derivation sidesteps that. He avoids the ad hoc quantization, and he achieves that seemingly simple result using stochastic electrodynamics, postulating that there's the 0-point fluctuation field. So that's really what the crux of this is. You don't have to really know the details of, oh, we do this sum of polarizations. We need to remember off the top of our head the integral identity from the fifth step of this derivation. How do we, justify invoking the resonance approximation? Oh, I forgot to do the change of variables, omega equals k times c. It's like you forget all that. At a high level, just think of how if the math works out, which I believe it does, it's not super difficult. It's not groundbreaking mathematics by any means. It is a bit of a pain in the neck, if you didn't have Hal Puthoff's paper, if you were just to say, okay, let's set out with from scratch, so to speak, and start with these stochastic formulations of Maxwell's laws, and let's try to oh god, how are we going to have the non-relativistic formulation for the equation of motion for this 1D charged harmonic oscillator? It's okay, Hal Puthoff has sort of done the heavy lifting to get to this result, and by the time we get to the discussion part of the paper, this will all, gel together, so to speak. But these 8 steps, I think this is what summarizes what the actual mathematical details of the derivation actually are. So that's what this paper is about. Now we can actually finally get into the paper itself. Okay, so here we are, ground state of hydrogen as a 0-point fluctuation, determined state, Hal Puthoff. And this is published in Physical Review D as of May 15, 1987, submitted on December 22nd, 1986. So here we have in the abstract, we show here that within the stochastic electrodynamic formulation and at the level of Bohr theory, the ground state of the hydrogen atom can be precisely defined as resulting from a dynamic equilibrium between radiation emitted due to acceleration of the electron in its ground state orbit and radiation absorbed from 0-point fluctuations of the background vacuum electromagnetic field, thereby resolving the issue of radiative collapse of the Bohr atom. So hopefully now, after my little presentation of slides in the beginning, that abstract has some context and some background to it. Let's get into it. Introduction. The key role played in 0-point fluctuations, ZPFs, in determining the behavior of certain quantum systems is such that the systems in question might properly be called ZPF determined. A simple but elegant example of a ZPF determined system is provided by the attractive quantum force, the Casimir force, between conducting parallel plates, where the force results from the redistribution of viable normal modes, and hence in the associated vacuum electromagnetic ZPF energy as the distance between the plates changes. Although essentially thought of in quantum mechanical terms, ZPF determined systems have successfully yielded to the analysis techniques of stochastic electrodynamics, SED, and I will note here, citations 5 and 6, those are these 2 papers here by Tim Boyer from the slides that I put the titles in here. So citations 5 and 6 from the Puthoff paper today are by both by Tim Boyer, Random Electrodynamics, the Theory of Classical Electrodynamics with Classical Electromagnetic Zero-Point Radiation, and General Connection between Random Electrodynamics and Quantum Electrodynamics for Free Electromagnetic Fields and for Dipole Oscillator Systems. This one, let's call it the 1975 Boyer paper, and then this is the 1975B Timothy Boyer paper. I'll mention, skipping over here onto the other side of the page, 1975B comes up with this m omega lowercase r squared equals 3/4 h bar results. It's on page 11 of the 1975B Boyer citation. I think that's number 6. Oh, I guess both of those papers constitute citation 5, but the second of them, which is in the citation, that's what I mean by 1975B. That one comes up with m omega r squared equals 3/4 h bar. I'll get into that. I'm not going to skip over to the other side of the paper. But anyways, citations 5 and 6 are important here. So continuing on, which treat quantum field particle interactions on the basis of classical concepts. In the SED formulation, one assumes that charged point mass particles interact with a background of random classical electromagnetic zero-point radiation with energy spectrum, as in the quantum mechanical case, given by rho of omega d omega is equal to a fraction with the numerator of h bar times omega cubed all over a denominator of 2 pi squared times c cubed then times d omega, which corresponds to an average energy of 1/2 times h bar times omega per normal mode. We're running out of dedicated wham. Oh goodness. Okay, we had too much stuff open at once. Anyways, it is of special interest that, as shown by Marshall and Boyer, the spectrum's cubic dependence on frequency can be derived solely on the basis of Lorentz invariance, since this spectrum is unique in its property that delicate cancellation of Doppler shifts with velocity boosts leaves the spectrum Lorentz invariant. So, reminder, Lorentz invariance means that the quantities remain unchanged by the Lorentz transformation, as I mentioned during the preamble slides. And as a reminder for those of you who don't know, the Doppler shift is a change in frequency or wavelength of a wave in relation to an observer who is moving relative to the wave source. Easiest way to remember what a Doppler shift is the way the sound of like a fire truck or ambulance siren changes when it's coming towards you or going away from you. That is an example of the Doppler shift. We also note that within SED, h bar appears in the above expression simply in the role of scale factor to align theory with experimental results. No quantum interpretation is required in its application, and all other appearances of h bar in the theory can be traced back to its appearance in this expression. So again, this derivation of the angular momentum energy of the ground state of the hydrogen atom, the derived expression is m omega naught lowercase r naught squared equals h bar, and you could say, oh well, h bar, that is a quantum quantity, but really we're not doing any ad hoc quantization in the underlying physics here, is what that just said. So thus the starting point for the SED formulation is seen to be parsimonious. Topics successfully analyzed within the SED formulation, that is yielding precise quantitative agreement with QED quantum electrodynamic treatments, include the Planck blackbody radiation spectrum, Casimir and van der Waals forces, and the thermal effects of acceleration through the vacuum. So again, Planck blackbody radiation describes the amount of electromagnetic radiation, that is to say thermal radiation, that a perfect opaque non-reflective object emits in thermal equilibrium at a specific temperature. Go check out my Gray Alien Discusses the Origins of Quantum Theory, the first video, if you want to know more about that. Casimir effect is, of course, the attractive force between two uncharged parallel conductive plates in a vacuum. This is the observation of what some might say is a truly quantum phenomena, but obviously by there being the obtainment of a precise quantitative agreement with the QED treatment of explaining the Casimir effect using an SED framework suggests otherwise, but van der Waals forces are the relatively weak distribution-dependent interactions between neutral atoms and molecules. It includes London dispersion, dipole-dipole interactions, and dipole-induced dipole interactions. So that's a little bit of AP chemistry perhaps there for you. And the thermal effects of acceleration through the vacuum, this is known as the Unruh effect, which is when an observer, when accelerating through a vacuum, perceives a background thermal bath of particles. So these are just to name but a few phenomena that have been, at the time of the publication of this paper in 1987, successfully explained by a stochastic electrodynamic framework. To name a few, all originally thought to be soluble only within the quantum formalism. We shall apply here the same SED techniques that have been used successfully in these previous studies. We also outline how the corresponding QED treatment leads to identical results. Of particular pedagogical interest for the insight it sheds on ZPF modeling within the SED framework is the determination of the ground state of the hydrogen atom. It is hypothesized that, at the level of Bohr theory, the ground state orbit is a ZPF-determined state, determined by a balance between radiation emitted due to acceleration of the electron and radiation absorbed from the zero-point background. In an early heuristic derivation by Boyer, a result m omega r squared equals 3/4 h bar was obtained. This is what I just referred to as 1975b. It's on page 11. This was considered close enough for the approach used to the desired m omega lowercase r squared equals h bar to indicate the basic soundness of the hypothesis. We present here within the framework of SED an alternative derivation that yields precisely the correct result for the ground state. Now we're at the main section. This is where the mathematical calculation of the derivation occurs. Steps what I call 1 through 8, referred to in the preamble of slides. So this section is titled Interaction of Charged Harmonic Oscillator with Zero-Point Background. In SED, the vacuum is assumed to be filled with random classical zero-point electromagnetic radiation, which is homogeneous, isotropic, and Lorentz invariant. Again, homogeneous, uniform at every point in space, and isotropic means that it's uniform in all directions. Every direction, and Lorentz invariant is unchanged by the Lorentz transformation, of course. Written as a sum over plane waves, the random radiation can be expressed as E superscript Zp in terms of the vector r and scalar t is equal to the real component of the sum over sigma starting at equal to 1 to 2 of the integral of d cubed k times the vector epsilon hat times the quantity, which is a fraction with the numerator, of h bar omega over a denominator of 8 pi cubed times epsilon naught. This quantity is to the power of 1/2, or the square root is taken of it, and the vector epsilon hat times the square root of this fractional quantity is then cross product with an exponent with an argument, which is I times the dot product of vector k with vector r, then minus I times omega t plus I times theta, which is in terms of the vector k and sigma. That was the stochastic electric field, which takes into account the ZPF according to the SED framework. So now we have the corresponding stochastic SED, that's redundant, but magnetic field formulation here. So we have capital H superscript Zp in terms of vector r and t. And again, vector r relates to the position within this field, t is the time. The magnetic field is equal to the real value of the sum over sigma from 1 to 2 of the integral of d cubed k, the cross product of the vector k hat with the vector epsilon hat, then times the square root of, or the half power of, the fraction with the numerator of h bar omega over a denominator of 8 pi cubed times mu naught, and then this is cross product with e with an argument of I times the dot product of vector k with vector r minus I times omega t plus I times theta in terms of the vector k and sigma. So in these relations, obviously epsilon naught and mu naught are the permittivity of free space for the electric and magnetic fields respectively. And let's just keep going. Let's not dwell on these too long here. Where sigma being equal to 1 or 2 denote orthogonal polarizations, the vectors epsilon hat and k hat are orthogonal unit vectors in the direction of the electric field polarization and wave propagation vectors respectively. So epsilon hat is for the electric field polarization, k hat is for the wave propagation vector, and then the function theta in terms of vector k and sigma are random phases distributed uniformly on the interval 0 to 2 pi, which are independently distributed for each vector k and sigma and omega equals k times c. Just reading that from my physical copy while I wait for my PDF here to scroll through because I have OBS open. So it's, as you can see, I closed like all my other tabs and everything else, and it still is kind of laggy. Anyways, it is an easy exercise to show that the Fourier compositions assumed in equations 2 and 3 correspond to the spectrum given in equation 1. So I'm not going to do that here for sake of time, but you could probably just type into your preferred flavor of AI and you can verify that the Fourier compositions assumed in the stochastic electrodynamic formulations for the electric and magnetic fields, which are in respectively equations 2 and 3 in this paper, correspond to the energy density spectrum relation omega of, or rho of omega d omega, which is what equation 1 in this paper is. We're not going to see equation 1 anymore in this paper. Like I said, we're just going to be doing the steps, which I called 1 through 8 in the preamble of slides, which get us from equations 2 and 3 to the m omega r squared equals h bar relation that we're shooting for here. So continuing on. Here, as in SED generally, the zero-point field is treated in every way as a real physical field and is taken to be responsible for the effects of interest. We begin our discussion of particle field interaction by considering a one-dimensional charged harmonic oscillator of natural frequency omega naught, located at the origin and immersed in zero-point radiation. For orientation along the x-axis, the non-relativistic equation of motion for a particle of mass m and charge e, including radiation dampening, is given by equation 4, which is m times x double dot, or the second time derivative of your position vector, or position relation, which is just given by x, then plus m times omega naught squared times x is equal to the fraction with a numerator of lowercase e squared over a denominator of 6 pi times epsilon naught times lowercase c cubed. Then that fraction is times x triple dot, the third order time derivative of your position vector, plus lowercase e, then times capital E superscript zp subscript x in terms of the vector r being equal to the 0 vector and at arbitrary scalar lowercase t for time. So this capital E superscript zp sub x is the x component of the electric field from the SED framework, which was given as equation 2. For clarity, obviously, lowercase e is charge E, and we have epsilon naught, that's the permittivity of free space, the electrical permittivity of free space. Anyways, substitution of equation 2 into equation 4 leads to the following expressions for displacement and velocity. We skip over to the other column and go up here. So equation 5, like I said in the preamble of slides, this is a displacement statement here. We have x equals e over m, then times the real component of the sum on sigma from 1 to 2 of the integral of d cubed k of the dot product between epsilon hat and x hat, then times the square root of the fraction with the numerator of h bar times omega over denominator of 8 pi cubed times epsilon naught. Then this integrand continues to be times 1 over capital D, and then cross product with e with an exponent argument of I times the dot product of k with r, then minus I times omega t plus I times theta in terms of vector k and sigma. Then we have our velocity statement in equation 6, which is v equals x dot. So we're just taking the first time derivative of equation 5, our displacement relation, to get e over m times the real component of the sum on sigma from 1 to 2 of the integral of d cubed k, then times the dot product of epsilon hat with x hat, then times the square root of the fraction h bar times omega over a denominator of 8 pi cubed times epsilon naught. Then we have times the fraction with a numerator of negative I times omega over a denominator of capital D, which then is cross product with e with an exponent argument of I times the dot product of k with r, then minus I times omega t plus I times theta, which is in terms of the vector k and sigma. And in the displacement and velocity equations, which are enumerated equations 5 and 6, capital D is shorthand for negative omega squared plus omega naught squared minus I times capital gamma times omega cubed, where capital gamma is equal to a fraction with a numerator of lowercase e squared over a denominator of 6 pi times epsilon naught times mc cubed. And again, further down, we don't really have to know capital D, but based upon an argument for the smallness of capital gamma, which here is equation 8, that's going to allow us to do some transformations, to do resonance approximation, and to expand the bounds of integration, which are going to be specified shortly here. We're going to be opening up the bounds of integration from 0 to infinity to negative infinity to infinity. So really, you just have to see that we have a displacement here, velocity, and then this shorthand quantity, capital gamma, will be invoked in a physics calculation argument, which is going to be coming here shortly. So from equation 2, which is our stochastic electrodynamic electric field formulation, and 6, which is our velocity relation here for our 1D charged harmonic oscillator, we now calculate the average power absorbed from the 0-point background as, and right here we have equation 9, which is a little bit of a behemoth. So we calculate this, and as I said in the beginning, quantities enclosed in angled brackets correspond to the expectation value or the average of what is enclosed in the brackets. So we have capital P with a superscript ABS. This denotes absorbed power. Power is of course defined as the dot product between the force and the velocity vector. Enclosing it in angled brackets, we're going to be taking the expectation value. This is because, of course, we have the stochastic phase terms in the formulations for the electric and magnetic fields given in equations 2 and 3. These were the theta in terms of K and sigma terms. So when we expand out the definition of power as the dot product of force with velocity, we have charge lowercase e times the electric field capital E superscript ZP corresponding to our SED formulation of the electric field. We have lowercase e times the electric field capital E dot product with velocity, and then we're taking the expectation value of this. So the third right-hand side of the equals sign here, we're just plugging everything into that definition of power. Everything else leading up to the so-called 8th step, which is in equating equations 18 and 19 at the very end of this section. We're all just plugging and chugging, crunching on this expansion of the definition for the absorbed power here. So, spelled all out, the expectation value or the average power absorbed from the 0-point background is equal to 1/2 times the real component of the entire angle bracketed quantity, which is E squared over M, then times the sum on sigma from 1 to 2 of the sum on sigma prime from 1 to 2 of the integral of d cubed k of the integral of d cubed k prime of the dot product of the vector epsilon hat with the vector x hat, then times the dot product of the vector epsilon prime hat with the vector x hat, then times the square root of the fraction with a numerator of h bar omega over a denominator of 8 pi cubed times epsilon naught. Then we have times the square root of the fraction with a numerator of h bar times omega prime over a denominator of 8 pi cubed times epsilon naught. Then times the fraction with a numerator of I omega prime over a denominator of capital D star. Star, of course, here denotes taking the complex conjugate, so we're going to negate the imaginary component, and D is that shorthand from equation 7. Continuing with the integrand, we have then taking the cross product of the foregoing components of the integrand we have with the exponent e with an argument of I times quantity vector k minus vector k prime, dot product with vector r, then minus I times quantity omega minus omega prime, close quantity, then times t plus I times theta in terms of the vector k and sigma, then minus I times theta in terms of the vector k prime and sigma prime. And that concludes the argument of the exponent in the integrand. Continuing on, it says where use of the complex conjugate and the notation 1/2 times the real component stems from the use of exponential notation. The behemoth, which is equation 9 that I just read, can, however, be simplified to the expectation value of absorbed power capital P is equal to 1/2 times the real component of E squared over M times the sum over sigma from 1 to 2 of the integral of D cubed K, Then we have, for the integrand, the dot product of epsilon hat with the vector x hat, then taking that dot product, squaring it, and multiplying it by a fraction with the numerator of h bar omega and a denominator of 8 pi cubed times epsilon naught, then times another fraction, which is I omega over a denominator of capital D star, or the complex conjugate of capital D. So we've simplified equation 9 down to equation 10, where averaging over random phases involves or involved the use of the relation, which is equation 11. We have the expectation of E with an exponential argument of I times quantity vector K minus vector K prime closed quantity dot product with vector R minus I times quantity omega minus omega prime closed quantity times T plus I times theta in terms of vector K and sigma. Then we have minus I times theta in terms of vector K prime and quantity sigma prime. That concludes the argument of the exponent. The expectation value of E with this exponential argument is equal to the Dirac delta function of sigma and sigma prime, then times the Dirac delta function of omega and omega prime, and then the cube of the Dirac delta function with an argument of vector K minus vector K prime. So as said previously, K denotes a wave propagation vector. So when we have this integral d3k, we can do this integral identity where we rewrite an integral which is in terms of d3k and rewrite it as d capital omega sub k times integral dk times k squared. So capital omega sub k is a polarization angle, I suppose. So now we can write our expectation value for the absorbed power as 1/2 times the real component of e squared over m times, and then we're going to be having two integrals that we're going to be taking the cross product of each of these integrals. So the first integral is the integral with respect to d omega sub k of the sum from sigma equals 1 to 2 of the square of the dot product of vector epsilon hat with vector x hat. So that's the first integral. We're going to cross product that with the integral of dk k squared times the fraction with the numerator of h bar omega over a denominator of 8 pi cubed epsilon naught, then times fraction with the numerator of I omega over the complex conjugate of the quantity capital D. So using that integral relation, we're able to rewrite our expectation value for the absorbed power. We're just plugging and chugging through. So following Boyer in citation number 14, we further note that with the sum over polarizations given by the sum on sigma from 1 to 2 of, we have our first square bracketed quantity of the vector epsilon hat in terms of the vector k and sigma, then dot product with the vector x sub I hat. We have closed the first square bracketed quantity. Then we have times this second square bracketed quantity, the vector epsilon hat in terms of the vector k and sigma, dot product with the vector x sub j hat, close square bracketed quantity. This is equal to Dirac delta function sub ij minus, we have quantity of the dot product of vector k hat with vector x sub I hat, closed quantity, then times quantity vector k hat dot product with the vector x sub j hat, closed quantity. So with the sum over polarizations given by what I just read, the angular integration in lowercase k takes the form of equation 14, which is where we have the integral of d capital omega sub k of the sum on sigma from 1 to 2 of the square of the quantity, which is the dot product of the vector epsilon hat with the vector x hat. This is equal to the integral d capital omega sub k of the quantity in square brackets 1 minus the quantity squared of vector k hat dot product with the vector x hat, close square brackets. This is then equal to 8/3 pi. The substitution of equation 14, this value of the integral with respect to d capital omega sub k being equal to 8/3 pi, substituting that into relation 12, which was our most recent formulation for the expectation value of the absorbed power. Substitution, as well as a change of variables to omega equals lowercase k times lowercase c, then leads to the expectation value of the absorbed power being equal to a fraction with a numerator of lowercase e squared times h bar over a denominator of 6 pi squared times epsilon naught times m times c cubed, then times the real component of the integral from 0 to infinity of a fraction with the numerator of I omega to the 4th power d omega all over a denominator of negative omega squared plus omega naught squared plus I times capital gamma times omega cubed. This is equal to a fraction with the numerator of lowercase e squared times h bar over denominator of 6 pi squared times epsilon naught times mc cubed times the integral from 0 to infinity of a fraction with a numerator of capital gamma, which again, that's given in relation or equation 8. We have capital gamma times omega to the 7th d omega all over a denominator of the quantity omega naught squared minus omega squared closed quantity squared plus capital gamma squared times omega to the 6th. Because of the smallness of capital gamma for a particle with the charge to mass ratio of an electron, for this case, the integrand given by equation 15 is sharply peaked around omega having a value of omega naught, or where omega equals omega naught. We can therefore invoke the standard resonance approximation, extending the limits of integration and replacing omega by omega naught in all but the difference term, which is seen on the denominator of the integrand of equation 15. This yields that the expectation value for the absorbed power from the 0-point fluctuations is equal to a fraction with a numerator of lowercase e squared times h bar times omega naught cubed all over a denominator of 12 pi times epsilon naught times mc cubed, then times the integral from negative infinity to infinity of 1 over pi times a fraction with the numerator of quantity capital gamma times omega naught squared over 2 closed quantity d omega all over a denominator of quantity omega naught minus omega closed quantity squared plus another quantity in the denominator, which is capital gamma times omega naught squared over 2 closed quantity squared. This turns out to just be equal to a fraction with a numerator of lowercase e squared times h bar times omega naught cubed all over a denominator of 12 pi times epsilon naught times mc cubed, which is to say that that integral from negative infinity to infinity is equal to 1. It just seems like we're integrating a normalized distribution over everything, so that's why it's just all equal to 1. So anyways, and it's the end of the sentence here. It says, since the Lorentzian line shape integral integrates to unity. So the Lorentz line is, I guess, the natural or homogeneous broadening of spectral lines. This quantity is formally given by capital L of x is equal to 1 over pi times a fraction with the numerator of omega over 2 over a denominator of quantity x minus x naught closed quantity squared plus quantity omega over 2 closed quantity squared, where x naught is the center or peak position and omega, I think it's w, is the full width at half maximum, and x, I guess, could be frequency, wavelength, or energy. So yeah, integral integrates to unity. So, in the result of equation 16, we thus have the final expression for the absorption of power from the random background 0-point field by a one-dimensional charged harmonic oscillator. We're almost done. We're basically at the 8th two-part step, which concludes the derivation here. So we now recognize that the Bohr theory ground state circular orbit of radius lowercase r naught constitutes a pair of one-dimensional harmonic oscillators in a plane oscillating in quadrature. We have here x equals x naught times cosine of omega naught times lowercase t. We have y equals y naught times sine of omega naught t, which is equal to x naught times the sine of omega naught t. And combining these into a radial term, we have lowercase r naught equals quantity x squared plus y squared closed quantity to the 1/2 power is equal to x naught. Therefore, the power absorbed from the background by the electron in circular orbit is double that of equation 16, or we have that the expectation value of the absorbed power for a circular orbit, subscript CIRC, is equal to a fraction with the numerator of lowercase e squared times h bar times omega naught cubed all over denominator of 6 pi times epsilon naught times mc cubed. That's the first part of the last step. The second part is that the power radiated by the electron in circular orbit with acceleration denoted capital A is given by the standard expression expectation value of radiated power capital P subscript CIRC to denote that it's for a circular orbit is equal to a fraction with the numerator of lowercase e squared then times capital A squared all over a denominator of 6 pi times epsilon naught times lowercase c cubed. This is equal to a fraction with the numerator of lowercase e squared times quantity lowercase r naught times omega naught squared closed quantity squared all over a denominator of 6 pi times epsilon naught times lowercase c cubed. This is finally equal to a fraction with the numerator of lowercase e squared times lowercase r naught squared times omega naught to the 4th all over a denominator of 6 pi times epsilon naught times lowercase c cubed. Under the hypothesis set forward by Boyer that the ZPF determined ground state orbit is set by a balance between radiation emitted due to acceleration of the electron and radiation absorbed from the 0-point background, we equate equations 18 and 19 to obtain that m times omega naught times lowercase r naught squared is equal to h bar. We have therefore, within the SED framework and at the level of Bohr theory, obtained the desired result for the ground state of the hydrogen atom. And that's it. So now we're at the discussion here. This is a short 4-page paper, so we're just going to continue reading it out here. We have seen that the ground state of the hydrogen atom can be modeled as a ZPF determined state. The hydrogen atom ground state thus takes its place alongside other treatments such as the Casimir and van der Waals effects as an example of a ZPF determined system successfully analyzed within the SED formulation. The net result of this effort is therefore to increase by one example the number of quantum phenomena that have yielded to the SED approach, while at the same time providing additional insight into the role of ZPF phenomena in determining basic quantum states. The significance of the derivation is twofold. First, with regard to the analysis technique used, the SED approach used here to solve for the parameters of the ground state of hydrogen as a ZPF determined state can be taken to constitute an example from the larger program, which generally goes under the heading of stochastic mechanics, as outlined, for example, by Nelson in citation 18. This larger program attempts to account for quantum fluctuations of particle states on the basis of randomizing physical interactions with a classical background field. Although the nature of the background field in stochastic mechanics is still considered to be an open question, like I said, this paper does not prove that there is this 0-point fluctuation background radiation EM field. Although the nature of the background field in stochastic mechanics is still considered to be an open question, Nelson, in citation 19, points out that the electromagnetic field, as used here and in related SED derivations, is a likely candidate, since a necessary requirement is that it be possible to construct a constant with the dimensions of action from the constants of the theory, and this requirement is satisfied in the definition of the fine structure constant, namely, alpha equals lowercase e squared over a denominator of 4 pi epsilon naught times h bar times lowercase c. The level of success obtained here in accounting for the hydrogen ground state on the basis of the stochastical electrodynamic approach would appear to provide additional supporting evidence for this viewpoint. Further development is required, however, to determine just how far the SED approach can be taken. Of specific interest is whether its success to date is due simply to the correspondence between classical and quantum treatments of linear systems such as non-relativistic harmonic oscillator states, or whether a more fundamental role for random classical electromagnetic 0-point radiation is implied. Indeed, for the problem considered here, in the corresponding QED treatment, the Heisenberg equations of motion in operator form are formally identical to the equations in this text. See citation 20, and quantum mechanical ensemble averaging leads to the same results. That seems like there could be some heavy lifting calculations to verify that. Thus, the SED treatment and conclusions presented here are reproduced without change in the corresponding QED treatment. Finally, it is seen that a well-defined precise quantitative argument can be made that the ground state of the hydrogen atom is defined by a dynamic equilibrium in which collapse of the state is prevented by the presence of 0-point fluctuations of the electromagnetic field. This carries with it the attendant implication that the stability of matter itself is largely mediated by ZPF phenomena in the manner described here, a concept that transcends the usual interpretation of the role and significance of 0-point fluctuations of the vacuum electromagnetic field. And that usual interpretation is basically what is implied by like a pedestrian interpretation of the Casimir effect. So the attendant implication carried by this derivation transcends that usual pedestrian interpretation of the role and significance of the ZPF in those other phenomena. So big implications, acknowledgements. Puthoff is indebted to Professor Timothy Boyer, City College of New York, whose lead Puthoff has taken, both for his original work along the lines discussed in this paper and for helpful correspondence. Puthoff also wishes to thank G.W. Church Jr. for valuable discussion during the development of this effort. And that's it. So it's a little short 4-page paper. As we saw, mostly comes down to crunching out that expectation value for the absorbed power from the 0-point background quantity here, taking it, plugging and chugging it through some relations which are pretty much following Boyer's lead here. And we have some interesting physics-based calculations going on here. This is something that from like a pure math background, it would be hard to just pull all of the steps off the dome here. But we have this really elegant boil down to the equating of the angular momentum at the ground state here being just equal to h bar. So that's really neat, really nifty. So yeah, I hope you guys enjoyed today's video. And yeah, let me know if you want me to do another read through, walkthrough of the other Hal Puthoff 0-point energy papers that I kind of pointed out in my preamble of slides. This could be like a little mini series, but hope you guys liked it. Like, comment, subscribe, leave a comment, especially if I said something that's incorrect or if I made a mistake, or if you have more of a physics background than I do. Please leave comments. I appreciate your feedback. See you guys in the next one. Peace.